So first thing we did in this unit was we talked about simple harmonic oscillators. We talked about a mass on a spring, and we talked about a pendulum. So the first kind of stuff that we did there had to do with the period of those two oscillators. So we talked about how for a mass on a spring, period was 2 pi times the square root of m over k. So the two things that could affect the period of a mass on a spring were mass and the spring, okay, and specifically the spring constant of the spring. For a pendulum, and we did a lab on this one to prove it, okay, a pendulum is affected only by length and gravity. It is not affected by mass, it is not affected by amplitude, okay? Those things have zero effect on the period of a pendulum, right? So expect that somewhere on the unit exam, you'll be expected to manipulate, solve problems to do with those formulas there. Okay, you'll also need to know a few of the kind of general principles of simple harmonic motion. Okay, you'll need to know about this. Okay, about restoring force, and that remember, if we're going to have simple harmonic motion, it needs to vary linearly with displacements. Okay, that is, the further from equilibrium the oscillator gets, the greater the force trying to return it to equilibrium, okay, in a linear relationship, which basically led us to Hooke's law, okay, because it was Hooke that kind of discovered that relationship for masses and springs. Okay, so with Hooke's law, okay, Hooke's law was that the force in a spring, or the restoring force, was equal to negative k times x. The negative being there to ensure that the force was always oppositely directed the displacement. So if the displacement was right, the force would be left. Okay, that's what the negative was there for. Expect that you'll probably have a few multiple choice questions about just the general nature of Hooke's law, but you will also have a problem in the written response that will ask you to solve something to do with Hooke's law. Here's the trick. Hooke's law and conservation of energy questions will give you similar information. The difference is, for most Hooke's law questions, and by most I mean like 95% of them, including the one on your test, okay, the object is not oscillating. Okay, if it's a conservation of energy question, the object has to be oscillating. Okay, but for a Hooke's law question, we just push on the spring or pull on the spring. We don't actually set it in motion. We measure the force within the spring. Okay, you can use Hooke's law with some conservation of energy questions, but in terms of the problem you're going to get, the object will not be oscillating. Okay, and that is one of the better ways to tell them apart. The other thing is that for a Hooke's law question, you'll only be given one displacement. In a conservation of energy question, you may be given more than one because you have to compare two different positions within the path of oscillation. Okay? With Hooke's law, you're only dealing with one spot. All right, then from Hooke's law, okay, we talked about conservation of energy. All right, so that's the same as it was before. EI still equals EF for a mass on a spring, for a pendulum, whichever. Remember that our potential energy for a mass on a spring is now elastic potential energy, which is 1/2 kx squared. All right, so we would solve one of these. It may be simple where it's comparing, the point of maximum displacement with the equilibrium position. At the point of maximum displacement, you only have what kind of energy? Potential, right? Because that's where x is its maximum and where v is what? When that mass is moved as far from equilibrium as it can, how fast is it going? It's not moving. That's where it changes direction, starts coming back. That's where the force is at its maximum, okay? Where the acceleration is at its maximum, but the speed is at 0, right? There's no kinetic energy at that point of maximum displacement, right? The equilibrium position is the exact opposite. At the equilibrium position, speed is at a maximum, and x is nothing, right? X is the distance from equilibrium. If I'm at equilibrium, I'm not away from it, and x is 0. Everyone following there? Okay, so just remember those kind of things. It's just like a roller coaster, except we're dealing with a mass on the spring instead. Okay, so we still have points of maximum kinetic, maximum potential, okay, and things like that. So we would set it up. Okay, we'd have 1/2 kxi plus 1/2 mvi squared equals 1/2 kxf squared plus 1/2 mvf squared. What you would have to identify is, are all four of those energies present at the two positions I'm dealing with? Or, if it mentions that one of those spots is the equilibrium position, then I don't have any potential energy there. Okay, things like that. Read the question carefully. Okay, other than that, it's not something you guys should have a lot of trouble with. It didn't give you trouble when we went over it, and when we did the assignment on simple harmonic motion. You guys didn't struggle with that at all, but just keep in mind, there's definitely going to be a question on conservation of energy, okay, a problem in the written response section. All right, questions there? Okay. Then we talked about waves, okay? We moved on to waves. And so for properties of waves, this is mostly terminology, okay? You're going to need to know things like what's amplitude, okay? What's wavelength, okay? What's period and frequency. You need to know the two kinds of waves. All right, and know examples of each type. Right, sound is a longitudinal wave, okay, whereas light is a transverse wave. Right? Water waves are a transverse wave, okay? Things like that. So know examples of each type. Okay. Also understand what waves are. Waves are energy, not matter. Okay. They're a traveling disturbance. Okay. Remember that it's not the medium that moves from A to B. It's the wave that moves from A to B. Okay. The medium simply oscillates either up and down or back and forth. Okay. Depending on which type of wave you are dealing with. Right. There could be some multiple choice questions testing your understanding of those concepts. Okay. The mechanics of or properties of waves. Okay, and then universal wave equation. Obviously, that's part of almost everything we did for the rest of the unit after we learned it. Okay, it's part of standing waves. It's part of air columns, right? It was part of, like, we had some echo questions and things like that. So expect that you'll get probably one question, one problem that'll have to do with just using the universal wave equation. And we talked about how that could be like, you have this many crests, but that's how many. If I have 6 crests, how many waves do I have? 5. Okay, things like that. Those little tricks, those could come back. Okay, remember about echoes. Okay, that an echo travels twice the distance between the objects because it travels there and back. Okay, little things like that are things that we'll need to keep, a close eye on, so we don't make silly mistakes. Okay, that make it seem like we don't understand when we do. Okay, so V equals F times lambda, or lambda over T, whichever, but you'll definitely be using that many, many times, okay? Once kind of for its own sake, and then obviously as part of other questions, okay, as well. Okay, interference. I told you there would be a question on the test where I would give you 2 overlapping waveforms and ask you to draw the resulting waveform. That's the principle of linear superposition. Okay, we add the amplitudes together, right? There's 2 kinds of interference, constructive, destructive. Okay, so this is going to be very diagram intensive. That's diagram, not piegram. Diagram. All right, so there's going to be some multiple choice, but also some written response stuff to do with interference. Okay, waves at a boundary, also diagram intensive. And almost exclusively multiple choice. right? So I maybe give you a before and an after picture of waves encountering a boundary, and then ask you something like, is the second boundary, or is the second medium more dense or less dense than the first? Okay, how do we decide that? If I have a wave, maybe I should draw a better wave than that. That was just, sorry. Okay, if I've got a wave encountering that boundary, how do I know um, based on its after picture whether the second boundary would be more or less dense? Right, so I look at the reflection. If it's more dense, the reflection will be inverted. If it's less dense, then it will be upright and usually small. Okay, the other thing I can look at is what does the wave look like in the new medium? Okay, so obviously a little while later, if this medium is more dense, I would have this. Okay, that big wave has now gotten shorter, smaller, and much of it was reflected back off of the boundary. Right, that would be an example of it that's more dense. So expect diagram related questions, plural, okay, on the unit exam for that. And then lastly, we have standing waves. Expect air column questions, okay, to do with that one. All right, so okay, definitely expect an air column question, and probably expect a couple of multiple choice questions about the nature of standing waves. Oh, something else about waves at a boundary. When we talked about waves at a boundary, we also talked about 3 behaviors of waves. Okay, remember that at a boundary, some is going to get reflected, some will be transmitted, okay, and that if it's transmitted, it might refract or diffract, okay, depending on, so I would say, again, diagram intensive, be able to identify, if I show you a wave pattern, are these waves refracting, reflecting, or diffracting, okay, based on the diagram itself. So again, diagram intensive stuff, multiple choice. Okay, and then standing wave problems. Oh, sorry. Air columns have to do with standing waves. Sorry, and then Doppler effect. Oh, totally forgot about that. That's what we did yesterday. Okay, there will be 2 questions in the multiple choice on that, and 1 problem in the written response. Okay, just like the ones we worked on yesterday. All right. Any questions you would like to ask about waves and simple harmonic motion? Okay. Yesterday, I posted both the unit exam and final exam review packages. So if there aren't any questions right now, I'm hoping some more will come up, okay, as you work through the unit exam review package. I don't know why, but I got like really gung-ho on the unit exam review package, and it's way longer than any of the others. I don't really know why. I think a lot of it's because this is so terminology related. So there's like 2 pages of fill in the blank sentences to, go over terminology and, wave behavior and stuff like that. Okay, and then there's some simple problems to do with diagrams, universal wave equation, things like that. So have a look through the package. You can decide what part of it you want to do first. Okay, but it's all useful. So you'll want to make sure that you're looking through all of it. Okay, so I'll put it up on the board, but it's probably easier for you to call it up on your phone so you can see whatever part of it you want. Okay. We're looking for the fundamental frequency. Okay, so we're looking for F of a 20 centimeter opened air column. So we know length is 0.2 meters and the air temperature is 18 degrees. Right, so we're going to go 332 plus 0.6 times T, okay, to get us our speed of sound. All right, so we're getting 342.8. And that'll be meters per second. Okay, so if we've got L, we can find the wavelength because we know that for an open air column, lambda equals 2L, right? So if we multiply this by 2, we have the wavelength. So the wavelength is 0.4 meters, and then we just use the universal wave equation. F will be V over lambda, so 342.8 divided by 0.4, okay, 857. What did they have, 855? Yeah. So that's what the difference is. Okay, any other ones giving us trouble? Okay, don't be afraid to ask, guys.